Hey everyone, and welcome to this explainer. If you've been following the latest in climate tech, you already know the holy grail right now. It's not just about reducing our emissions, it's about finding a system that actively and affordably cleans the air that's already out there. Well, today, we are looking at something truly fascinating. We're going to take some raw, unfiltered engineering blueprints and translate them into reality. We're talking about a piece of technology that's aiming for a staggering 99.99% purification of the atmosphere. It's bold, it's dense, and we're going to break the whole thing down together. Okay, so here's our roadmap for today. We're going to cover the air curtain concept, take a look inside the atmosphere scrubber, check out the building of the pipe reactor, examine the actual CO2 crusher prototype, and finally, we'll run the economics of carbon capture.
All right, Section 1, the air curtain concept.
This raw chemical sketch reveals the sheer, staggering ambition of this project. What we're looking at is the initial schematic for what the designer calls an air curtain scrubber. And if you look right at the top, the explicitly stated goal is 99.99% purification of the atmosphere. I mean, that is not a small claim, right? To actually pull this off, the system relies on a continuous, multi-stage reaction sequence, all housed within an 8-meter-long vessel. The audacity of mapping out a near-total atmospheric purification system on a single piece of paper is just incredible. But as you'll see, the chemistry outlined here is highly specific and deeply, deeply structured.
So to really understand how this air curtain works, we've got to cut through the jargon and look at the core mechanism driving the whole machine. The entire system is built around these things called oxidant producers. Essentially, think of them as chemical emitters that spray 3 highly reactive oxygen species into a mist. They mix specific oxygen ions with water to create this reactive fog. And that fog physically breaks down and neutralizes different types of complex pollutants as they pass through. It's literally like a localized, high-intensity chemical storm designed to just completely strip the air of unwanted elements.
Moving on to Section 2, inside the atmosphere scrubber, let's actually shrink down for a second and narratively follow a molecule of contaminated air. The purification process happens in 3 very specific sequential stages, all moving along a vessel that's positioned on a precise 3% slope. First up is Step 1, the shock oxidizer. Here, an O+ species is mixed with water by a sprayer to create an OH+ mist in the first reservoir. This initial shock is specifically tailored to knock out the heavy hitters, things like CO2, ammonia, and sulfur. Then the air flows into Step 2, which is the broad spectrum step. Using an OH* mist, this stage targets a totally different class of complex pollutants, including VOCs and formaldehydes. Finally, in Step 3, the air hits a neutralizer reservoir. This uses an O- species to scrub absolutely everything else before the air passes through a final carbon filter. Plus, each of these stages has its own wet recovery system to capture all those neutralized compounds.
Section 3, building the pipe reactor. Now, this structural engineering pipeline takes that concept and sketches out a machine designed to process a massive 1 ton of air per hour. It maps out a 3 by 12-foot pipe reactor, complete with intake fans pulling in 500 cubic feet per minute. It shows the exact sequence of the internal environment. We're talking the integration of a heat pump running at 90 degrees Celsius, alongside compressors running at 12 psig, and dryers. It basically takes that theoretical 3-stage chemical process we just talked about and forces it into a linear engineered tube that's built for continuous industrial throughput.
And this is probably my favorite part, because it brilliantly illustrates the practical realities of actually building this thing. The designer takes those handwritten math scribbles and neatly breaks down the exact, off-the-shelf costs of the physical parts. We are not looking at some theoretical, priceless unobtainium here. We're looking at a $6,000 pipe reactor with $6,000 in fittings and misters. There's a $2,000 intake fan with a $2,000 mount, a $4,000 dryer, a $1,000 compressor. By breaking down the raw component costs like this, the schematic strips away all the mystery of climate tech and reveals it as a totally practical, achievable plumbing and HVAC challenge. All right, Section 4, the CO2 Crusher prototype. Okay, this is a really crucial moment in our explainer. What we have here is a photograph of the actual physical CO2 Crusher prototype built by Reduction Tech Inc. in 2024. This proves that this technology isn't just some theory sitting in a notebook. This is a fully constructed, bolted-together prototype that is drawing high-voltage power and processing gas right now. You can see the heavy industrial steel of the main reactor body, the intricate wiring, the pressure gauges, and the heavy-duty PVC piping extending vertically. It is the tangible, real-world realization of those hand-drawn blueprints. And translating all that dense jargon into tangible hardware modules reveals the reality of the machine. The power supply for DLC deposition is sitting right alongside the wiring on the floor. A sublimation column is mounted directly to the side piping. There's the HT element power feeding straight into the top of the main reactor core, and a very specific exhaust pipe labeled Oxide Radical to Outdoors. Seeing these highly technical labels literally taped and pointing to actual steel and wires, it just really highlights the incredible leap from the handwritten math of oxygen producers to a fully functioning specialized machine. Finally, Section 5, Economics of Carbon Capture. Let's talk numbers. So the schematics estimate a $1 million build cost over the span of 1 year. The notes actually detail a path moving from a $400,000 prototype to a setup with modified CO2 crushers. That $1 million figure represents the capital expenditure required to really scale this up. And honestly, in the grand scheme of industrial climate infrastructure, where facilities often cost hundreds of millions of dollars, $1 million for a commercial scale build is a remarkably lean projection. And in return for that investment, the math projects a massive 91,000 CO2e captured per year by this modified setup. That is 91,000 tons of carbon dioxide equivalent processed and removed from the atmosphere annually. To put that into perspective, that's roughly the footprint of taking 20,000 passenger cars off the road every single year. When you look back at the 3-stage chemical scrubbers, those 500 CFM intake fans, and the continuous flow design we explored earlier, you really start to see how the designer mathematically justifies hitting such an aggressive annual capture rate. Which brings us to the crucial point. This final, absolutely staggering projection, reducing the cost of carbon capture to just $11 per CO2e. $11. For a little context, many current direct air capture technologies struggle to get their costs below several $100s per ton. If the off-the-shelf parts, the 3-stage oxidant misting process, and that $1 million build-out scale exactly as these handwritten notes calculate, well, this represents an absolute paradigm shift in the financial viability of cleaning our atmosphere. So, I want to leave you with this final thought to consider. We've traced this whole journey from a radical hand-drawn concept targeting 99.99% purification through the off-the-shelf math of pipe reactors, right up to a physical steel prototype buzzing with high voltage. The ambition hiding inside these rough schematics is completely undeniable. But the ultimate question remains. If this system can truly deliver carbon capture at just $11 a ton, are we looking at the exact blueprints that finally makes global atmospheric purification an economic reality, rather than just an environmental dream? Thanks so much for joining me on this explainer, and remember to keep questioning the blueprints of tomorrow.